Okay, welcome back after the break. Today we will continue our discussion on. So, we were discussing about controllability and observability in the previous class. We want to move to the next step, natural next step, which is controller design, which is how do you design controllers for systems for linear systems. Generally speaking, people tend to use linear controllers for linear systems because in some sense they are optimal if you have quadratic cost function and so on. I'm not pretty sure whether we are doing any optimization in this particular. Uh, no, I don't think we are doing any optimization in this class. Um, but in some sense, linear controllers are good enough for linear systems, and therefore we'll be talking about how do we design controllers, so observers and controllers for linear systems uh, to be able to get desirable output from linear systems. But before we do that, I wanted to talk about some standard forms for linear systems. So today we are going to talk about, and unfortunately, I left my notes in my classroom, so I have to read from the book. But we are going to talk about Kalman's decomposition theorem, controllable companion form, and observable companion form. So these are the three standard forms of control systems that we will talk about. And the core idea is actually very simple. You have the original control system where you derive the dynamics of the control system of the linear system using physics or chemistry or biology. You want to do a similarity transform of that particular system to some other system where the A matrix, B matrix, C matrix has a very specific structure. And then hopefully you will be able to exploit that structure to be able to come up with a controller for that system. So the control design part, we'll talk about it later, but hopefully we can exploit that structure in order to design the controller, and that will help us achieve our objectives of being able to design a controller for that system. So the goal for today's class, and it's just going to be today's class, is to go from the original system dynamics to a specific structure of A, B, and C matrices so that we can better design the controller for that particular system. And remember that through similarity transform, if you have a linear control policy of this updated new system, new phantom system that you've created, you can actually pull back that linear policy into the original state space and the original observation function to be able to solve the problem that you are looking to solve. So I know it's a bit vague right now, but we'll make it concrete as time progresses. Okay. So let's consider. So this is chapter 6 of the book. And I want to remind you what we did in the previous lectures, so that way we have some of those results handy. So I have x dot t is equal to axt plus but so that's my system equation. The controllability matrix was given by B. The observability matrix was given by C, CA, CA raised to n minus 1. And then the range of C was denoted by RR. And it was called reachable / controllable subspace. And the null space of the observability matrix was denoted by RO bar, and this is unobservable. unconstructible subspace. And we have seen examples of that in the previous lectures. Okay, so there will be, like, this is your Rn, and so there is a subspace in Rn, possibly passing through origin, and this is my Rr. So this is the set of states that I can reach and I can control. I can control in the sense that I can get to the origin by applying appropriate control. So that's what controllability means. And then there would be some other subspace containing 0. This will be the unobservable subspace. And if you have a state, initial state in one of those within that subspace, there is no way for you to be able to differentiate that point with the 0 point. So you don't know where exactly within this particular subspace you lie. So there will be a lot of confusion about the unobservable subspace. So if you start from some point in the unobservable subspace, you won't be able to identify where exactly you lie within that particular plane. Okay, any questions so far? Okay, so remember that this construction was for general A, B, and C matrices, right? So D directly gets multiplied to U, so we don't quite care much about D, but we do care about the A, B, C matrices. And what I'm going to tell you today is I can do a similarity transform. I can get my x hat dot t equals to a hat x hat t plus b hat ut and yt equals to c hat x hat t plus d hat ut. Turns out d hat will be equal to d, but I want to make sure that I'm using consistent notation. So I'm going to do a similarity transform of this particular system to this particular system, x hat 0. So I'm going to do a similarity transform to get this a hat, b hat, c hat, and d hat matrices, where a hat, b hat, and c hat will have a very specific structure. That's the goal today. And the way I'm going to structure this x hat in the coming discussion, in the most general situation, I want to differentiate within x hat. I want to have some coordinates that are controllable and observable, some coordinates that are controllable but not observable, some coordinates that are uncontrollable but observable, and some coordinates that are unobservable and uncontrollable. Okay, so I want to convert this x hat into a bunch of components which lies in this space, lies in the other space, lies in this space, and lies in the other space. And so that way I can clearly see what's happening by looking at the a hat, b hat, c hat, d hat matrices. And more importantly, once I have that structure, I can design a controller to get some desirable characteristics of x hat, for instance, stability, and then I can pull that expression back into this equation and get the appropriate control policy for the original system. Okay, so that's the goal. Let's start. Yeah, any question? No? Okay. So let's start with the standard form for uncontrollable system. I'm going to define a matrix. So, okay, so my rank C NR. So this implies, and this NR is strictly less than, let's assume that this is strictly less than N. If it is equal to N, you can be in the same original matrices are good enough, but assume for now that my NR is strictly less than N. So the rank of C is equal to NR, and that's less than N. So this implies that there exists V1 to VR, VNR in basis of RR. How do you get the basis vectors for RR? If I were to ask you that I want a bunch of basis vectors, it doesn't have to be orthogonal, it just has to be basis. It has to be able to span the entire RR. What would you do to get this basis? Any idea? So I have this matrix. This matrix, it's of rank NR, okay, which is strictly less than N. And I want to get NR basis vectors for the subspace RR. This is the RR. It's the range space of C. What would you do to get that basis? Yes. That's one way to do it, but I want a simpler approach to do it, to get there. So eigenvectors, so if this matrix is large, eigenvectors is going to take a long time it'll take a long time for you to be able to compute the eigenvector. Any other idea? So remember that the range of this matrix, the range of this particular matrix is going to be the sum of columns of this matrix, right? And I want to extract NR linearly independent vectors out of these columns. That will get me the basis for the RR, the reachable subspace. So I'm going to look at the columns of B. Whatever are the linearly independent columns, I'll pull them out. Then I'll look at the columns of AB and look at the linear independence with respect to the columns that I've already taken out, right? And then so on and so forth until I've gotten the NR columns from the matrix C. Okay, that's going to give me a basis for RR. You can be more fancy, you can come up with orthogonal basis, you can come up with more complicated basis like eigenvectors as somebody suggested. But the simplest way to do is just look at the columns of this matrix and figure out NR independent, linearly independent columns, and that becomes your basis for RR. Now I'm going to define a matrix Q V1 to VNR and then some Qn minus NR. So these are the basis vectors and these are linearly independent of V1 to VNR. So you pick some other random matrix, just pick a random matrix which is linearly independent of V1 to VNR and make sure that this matrix Q is in Rn cross n and this is full rank. Okay, so I have an uncontrollable system. What that means is my rank of C is NR, which is strictly less than N. If the rank was equal to N, then it's a controllable system. I don't have to worry about it, but right now I'm in the uncontrollable system domain. So I extract nr number of columns of C to get linearly independent vectors that forms the basis for RR. Then I fill this the empty part of the matrix, I filled it up with some other vectors that are linearly independent of V1 to VNR. And now what I have created, all of these are linearly independent set of vectors, as a result of which my matrix Q is full rank. A full rank matrix is invertible. Okay, so now I can define my A hat to be Q inverse AQ, and my B hat to be Q inverse B. This should look like a Q. I want to erase some part. Okay, let me erase this side. Okay, so what does lemma 6.1 say? I'm not going to do the proof of this lemma, but I think this is interesting, so we'll look at the A hat 1 1, A hat 1 2 0, A hat 2 2, and B hat 1 0. This is NR n minus NR. The key idea in the proof is that A RC equals to RC. And this would imply that AQ equals to QA hat. That's the core idea. So by appropriately picking the elements of these matrices, you can show that this condition is satisfied, and the same thing can be done for B hat as well. So you can construct this matrix B hat and A hat such that these conditions are satisfied. And the reason for that is that the range space of the controllability matrix is, if you multiply any element here by A, you essentially get an element back in RC, the range space of the controllability matrix. Right? So this is a matrix. I'm going to multiply the matrix with any vector within this subspace. I get another vector. It doesn't have to be the same vector, but I get another vector within that same subspace. So the way it's written is A gets multiplied to a set, and you get the same set. Okay, so it's somewhat of a set notation, not necessarily a element notation, but what this essentially means is RC is equal to AX, X in RC. It's the same thing. These two are essentially the same idea. And this idea can be established using Cayley-Hamilton theorem. Okay, so I won't go into the details of the proof, but the proof is there in the book. Rather, I would say like a short proof is there in the book. So you can take a look at that if you're interested. But the key idea here is you apply Cayley-Hamilton theorem to establish this result. And we actually have talked about this result in the previous lectures. And then from this result, you can get to this particular result through this particular construction of the Q matrix. Any questions so far? Okay. So I get this A hat and B hat matrix. Let's see what the controllability C hat for this particular matrix look like. Has everyone written it down? Okay. Let's compute C hat. It's B hat 1 0. And then what is A hat B hat? Can someone tell me what A hat B hat looks like? Does this look correct? Right, so we have the exactly NR rows. I have NR rows that are non-zero and N minus NR rows that are completely zero. Okay, that's what it means to convert the original system into standard form for uncontrollable system. Okay, I have the original system. I converted it into a standard form for uncontrollable system. I get system matrices that look something like this, and it becomes so easy. Okay, so let's look at what the X hat T looks like under this particular system. Okay, so this is I would say fact number 1. Let's look at fact number 2. Any questions so far? Fact number 2. So I'm going to replace X hat equals to X hat 1, X hat 2. Then I get X hat 1t, X hat 1 dot t. Oh, So after I converted the original control system into the standard form for uncontrollable system, what I notice is that the ut term seems to be influencing x1, but it doesn't influence x2 at all, right? So x2t is no ut term here. So I cannot control x2 hat at all. x2 hat has its own dynamics, and it will converge to, or maybe not converge, diverge to whatever point it wants to go to at its own pace according to this particular matrix. And in fact, this x hat 2 tends to influence x hat 1 through this particular matrix, right? So even though you are able to control x1 hat, if x2 hat is going to infinity, your x1 hat is bound to go to infinity. Okay, there's nothing you can do to prevent that from happening if this particular system or subsystem is uncontrollable and is unstable. So if this term is going to infinity, it's going to influence your dynamics for x hat 1, and then x hat 1 will go to infinity. So if you are in this situation, you want your a hat 22 to be stable. You want the eigenvalues of a hat 22 to have negative real part, strictly negative real part, so that this term will go to 0, so that this term will eventually become 0, and you are able to control x1 appropriately. Okay, any questions so far? Awesome. Let's look at fact 3. What is e raised to ATB? Yes, please.
Sorry, where did you get x hat from? Is that just
this one x hat?
No, the original x hat where you separated it into x hat 1 and x hat 2.
Oh, this x hat is this one.
But is there some conversion with q similar to the
okay, so the way to the way these two are connected is x hat of 0 would be q inverse I want to make sure I'm writing it correctly. Yeah, x hat is q inverse xt. So the connection between x hat and x would be x hat t equals to q inverse xt. But I do want to make a note here that this is the connection. This is how you go from one space to another, but this is not how you compute x hat t. X hat t can be computed in this particular way by solving this differential equation, and it will turn out that these two are actually the same. Okay. So this is the same as q inverse e raised to a hat t q. No, it's q a hat q inverse. Okay, let me write it the other way. So a hat was q inverse aq. So e raised to at is q e raised to a hat t q inverse. And so e raised to at times b is q e raised to a hat t q inverse b equals to q e raised to a hat t b hat. Now let's focus on this expression. e raised to a hat t b hat. Can someone tell me what this expression is going to look like? You know, there is a complexity here, which is what's the exponential of a hat. So a hat has this particular structure. What's the exponential of a hat? And it will turn out, where can I write it? Maybe I'll erase this side. Okay, so you will have the exponential term for a hat 1 1, you will have exponential term for a hat 2 2, but you will have some complicated matrix here. It's not going to be simple and straightforward, it will be some very complicated looking matrix, MT. But I don't care, because once I multiply it by B, what I will get is e raised to ATB equals to Q e raised to a hat 1 1 t b 0. Oh, b hat 1. So everything has a structure in the new system, in the standard form for uncontrollable system. Any questions so far? Okay, so by putting things in the standard form, you're able to get a very specific structure of A hat and B hat matrices, which simplifies the controllability matrix. It simplifies understanding which states, or at least in the new state space, what are the states that are influenced by actions and what are the states that are not influenced by action. And you can clearly see that x2 hat, it doesn't contain action, so no matter what action you pick, there is no way you can influence x hat 2t. It has its own pace and it will evolve according to its own dynamics, but it will influence x hat 1, and therefore you can do something to influence x hat 1, but you can do nothing to influence x hat 2. And so even in the matrix exponential thing, you can observe some of this behavior again and again. In our body, what is a thing that you can observe? What is a state that you can observe but you cannot control? You know, heartbeats. I cannot control my heartbeat. I can't make it go to 0. I can't make it go to infinity. It is what it is. Okay, but I can observe it. I can take a pulse and I can observe my heartbeat, but I can't really influence it. So it's part of that uncontrollable subspace. It does influence a lot of my other body functions, body states, but it has its own pace, and I cannot influence that pace. Okay. Any questions so far? Perfect. So that talks about the standard form for For uncontrollable systems, let's talk about standard form for unobservable systems. And then I'll connect the two of them and create a Kalman decomposition theorem. So let me erase this part. So in this case, you have the null space of the observability matrix is n minus no dimensional. Oh, so rank of O equals to no. So the null space the dimension of null space of the observability matrix is n minus no. So I get the basis vectors for this. And I'm going to define my Q matrix as Qn0 and lemma 6.4. Okay, lemma 6.4 in the book, which says that A hat is of this form: A hat 110, A hat 21, A hat 222, and C hat is of the form C hat 1, 0. This, I believe, should be n0 dimensional. And this is the standard form for unobservable system. With the same set of facts, whatever facts we talked about, some similar facts would also apply to this particular new system. B hat is Q inverse B. I don't care what B hat looks like because all I care about is the observability. And what you will notice is that YT would be dependent on X hat 1T only. Okay, so I cannot contain, so YT doesn't contain any information about X hat 2T, even though X hat 2T might influence the behavior of X hat 1T, but I cannot find out what X hat 2T is going to look like on the basis of the information about YT. Okay, once again, the reason for studying these systems will become clear when we talk about observer design and controller design. So right now it might look like an abstract thing that we are converting one system to another system. But when it becomes, when we talk about controller design next week, the reason for studying and putting this thing in this form will become very clear. We'll take a system, we'll design a controller for the standard form, and then we'll pull the controller to the original problem statement. Okay. So what we have talked so far is you have an uncontrollable system, you can put it in a standard form. You have an unobservable system, you can put it in the standard form. What you have a system which has both controllable and uncontrollable subspace and observable and unobservable subspace. So you have like 4 different quadrants, right? So you now have to decompose the system into a 4x4 subsystems where you will have controllable, observable, controllable, unobservable, unobservable, controllable, and so on and so forth. So that's called Kalman decomposition theorem. Any questions so far before I erase this part? Okay. This is theorem 6.6. in the book. So if you have uncontrollable and unobservable subsystems, then AB uncontrollable, AC unobservable implies there exists Q in Rn cross N. A hat equals to Q inverse AQ. B hat equals to Q inverse B. C hat equals to CQ. And D hat equals to D, such that I'm going to remove hat from the inside of matrices. Okay, so what did we do? We have the original system that was uncontrollable and unobservable. It had non-trivial uncontrollable subspace and a non-trivial unobservable subspace. I can do a similarity transform of the system through this particular matrix. So there exists a Q. How to construct the Q? It's there in the book. It's a very complicated Q matrix. By taking the appropriate basis for the range space, intersection of range spaces and unobservable subspaces and so on, you can construct this matrix Q, which will have this particular format of A hat, B hat, and C hat matrices, wherein you can see that the X hat 1 and X hat 2 have inputs from the controller, but X hat 3, X hat 4 has no input from the controller. Y hat can, or Y can observe X hat 1 and X hat 3, but it cannot observe X hat 2 and X hat 3, right? So you have decomposed the system into 4 different quadrants, and your X hat 1, X hat 2 belong to the controllable quadrant, X hat 1 and X hat 3 belongs to the observable quadrant. So X hat 2, so X hat 1 is in both controllable and observable. So you can both control and observe X hat 1. X hat 2 you can control, but you cannot observe. Okay, you cannot get any information about X hat 2 even though you can control it. So think about it like my back. I cannot see my back, I cannot observe it. In fact, no person in the history of the planet has been able to see its back. Isn't that very nice fact to know? Well, so I cannot observe it, but I can bend my back. I can control it, but I cannot observe it, right? So that's X hat 2. X hat 3 is uncontrollable but observable. So something like a pulse rate, I cannot control my pulse rate, but I can observe it. I can take my pulse. And X hat 4 is neither controllable nor observable. I can neither control it nor can I observe it. So something like my liver function. I cannot control it, I cannot observe it. It is what it is. I don't know if my liver is acting up well today or not well today. There is no way for me to know. right? It's unobservable and uncontrollable. I cannot tell my liver that, okay, excrete more, I don't know, some fluid into my bloodstream. It's supposed to do that. I hope it is doing its job properly today, but there's no way for me to observe. There's no way for me to control. And my hands are both controllable and observable. I can control my hand and I can observe my hand. I can observe what it is doing. Okay, so Kalman came up with this decomposition back in 1950s. Kalman was very active in 1950s and 60s, so I presume this theorem is from that era. And anybody knows why people were studying linear systems back in 1950s? What was the burning problem of 1950s? Moon landing, yeah, kind of. So it was precursor to moon landing. So anything related to rockets, aerospace, all of this stuff was actually very useful. And so people like Kalman were actually professors looking into aerospace applications, and the computers of 1950s, whatever they looked like, could only do matrix multiplication. And so that's why they were trying to do things with respect to matrices. And they did reach the moon, so I guess they were successful in doing that. Okay. Wonderful. So that completes our discussion on Kalman decomposition theorem. Now I want to talk about the controllable companion form. Any questions so far on this? Okay. The proof is not there in the book for theorem 6.6. So the statement is given, the proof is not given, but the author has provided references for the proof. So if you're interested, you can go back and look at the proof. But I've covered all the important results that leads us to the proof. The Cayley-Hamilton theorem, the invariance of the unobservable subspace by multiplication of the matrix A. And those are the information that is needed in order to prove results of this type. Okay. So now I want to talk about controllable companion form. So Kalman decomposition theorem is just one way to get a similarity transform of the system in an appropriate format. The next one is controller companion form. Controllable companion form. Controllable companion form. I have seen some paper/book replacing companion with canonical. I think it means the same thing. I don't know why people are calling it different things in different books, but you can think of them and you can use them interchangeably. The book calls it companion form, but I myself have taken a course where we called it canonical form, controllable canonical form. Who knows what the right terminology is? I'm going to assume that U is one-dimensional for this discussion. So I'm going to assume that U is in R, and I want my B hat matrix to be of this form. I want something like an identity matrix at the bottom of B hat. That would make it a controllable canonical form. So this is desired. So people studied this, and so I'm going to give you the result. Let me say okay. I'm going to define my A hat let's define my P matrix. So let me define my P matrix as follows. Okay, so even before we go to the P matrix, let's say my C matrix is B, AB, A raised to n minus 1B. This is in Rn cross n. So this is in Rn cross n because my U is in R. So each of this is single dimensional vector. I mean, one dimensional. It has one column. I have n columns, so it is Rn cross n. Let's say Q, last row of C inverse. This is a controllable system. C is full rank. So now I have a controllable system. I have C which is full rank. I can invert the C matrix and I can pick the last row of C inverse, and I can construct the matrix P as Q, QA, QA raised to n minus 1. And I'm going to define my matrix A hat as PA, P inverse. Okay, so I pick C inverse, I construct this matrix P, I do PA, P inverse. So remember in the previous one, A hat was Q inverse AQ, but now the way I have done the construction, it's PA, P inverse, so slightly different. And B hat is equal to PB. And turns out B hat is going to be 0, 0, 0, 0, 1. So 1 is at the last, it's the last element of the matrix B hat. And then A hat would be given by 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. And the last row is going to be minus alpha 0, minus alpha 1 minus alpha n minus 1. So these coefficients, these elements are coming from the eigenvalue, the characteristic polynomial of the matrix A. That's leading us to the last row of A hat matrix. Okay, I've done it for the single input case. You can do it for multi-input case where you have some sort of identity matrix in the B hat matrix. The construction is given in the book. The construction is extremely complicated, but the eventual goal is that I want to get B hat in some specific form for a situation where you have a completely controllable system. And so if you want to get V hat of a specific form, then A hat can be given by this particular matrix. And let's try to unpack what does this matrix looks like. So I have x hat dot t equals to A hat x hat t plus B hat ut. So let's see, I'm getting x hat 1 dot t. What is x hat 1 dot t? What is x hat 1 dot t? It's x2 hat t. x2 hat dot t is equal to x3t all the way up to x hat n dot t equals to minus alpha naught x hat 1t minus alpha 1 x hat 2t minus plus ut. So ut influences x hat nt, x hat nt influences x hat n minus 1t, and that's how the influence travels all the way up to x hat 1t. Right? So the action here is actually controlling one state. It's influencing one of the states, the last state in the system, in the new system. But that particular state is influencing the previous state, that state is influencing the previous state, and so on. So that's how the influence is going all the way up to the initial, the first element of the x hat t. And so this one is known as controllable companion form. This is for controllable system. If I have an uncontrollable and an unobservable system, I go to the Kalman decomposition theorem and I get this complicated 4x4 structure of the new state space. For controllable system, I can get B hat in a way that it looks like 0, 0, 0, 0, and then 1. So the identity structure appears at the bottom of the B hat matrix. So that's for controllable system. And you can have the similar idea of observable companion form or observable canonical form, where you do something very similar and C hat looks like identity and 0, 0, 0, 0, 0 all the way to the end. Let's do the observer form. Any questions on this? Okay, so you can do a similarity transform and you can get the matrix A hat and B hat in this particular format, and that allows you to think of the system in a completely different way, where you are able to observe how the influence flows within that particular system. Yes, please.
Is there any instance where someone would want to use this to build an intuition about their system, or is this all for the future controller design that we're going to do?
Extremely good question. So, have you taken feedback control systems in mechanical or in aerospace or in ECE? No?
My background is computer science.
Oh, okay. Your background is computer science. Okay. So, in 3551, which is the ECE 3551 feedback control systems, so of course, the use for this particular thing happens when you are doing controller design. So for instance, if you have a controllable system, let's say you have a controllable system, you design the controller for this particular system. So you assume the structure of your A hat and B hat matrices, you design the controller, then you pull that controller back into this particular domain and you apply that control action here. So when you're doing feedback control system 3551, you actually are the denominator in the transfer function is essentially coming from the coefficients that are here, and the numerator, anyways, there is connection, but I have not made that connection explicit in this particular lecture, because then we need to do transfer functions of matrices and so on. I don't want, you can technically do transfer function of this particular matrix, but because we don't assume people have taken 3551, I'm not doing the transfer function stuff in this particular class. But there is a connection to 3551, which I'm not being explicit here about. And the controller design part that we will talk about in the future, the way this thing gets connected there is we design the controller for this, and then we will use that controller for that particular system. So let me give you a very quick peek into that. Okay, so let's say I have a system like this. Somebody gave me this system. It's a rocket that's supposed to go to Mars. Somebody told me that, look, this system is controllable. Okay, now I have to design a controller for this controllable system. These matrices are pretty complicated. Okay, I don't know how to design a controller by looking at the matrix. What I can do is I can do the controller, I can assume that the matrix looks like this. Okay, so let's say I'm going to assume that my x hat dot t equals to a hat x hat t plus b hat ut, and somebody gave me the specification. I'm able to meet that specification for the eigenvalues of the feedback. Okay, what's the feedback control? So let's say my ut equals to minus k x hat t. So k is the gain matrix, it's called the gain matrix, and I'm going to multiply it by x hat t, and that's going to give me my ut. So this is a hat minus b hat k x hat t. So what is controller design? So controller design, to some extent, is trying to make sure that the eigenvalues of this matrix satisfy certain criteria. Okay, so either you want to make the system stable, or you want to change the overshoot characteristics of the systems or undershoot characteristics of the system, or rise time or settling time, and so on, things that you cared about in 3551, but we haven't talked about it yet. But essentially the controller design is the identifying a matrix K such that the eigenvalues of this composite matrix satisfy certain criteria. Wonderful. By assuming that A hat and B hat is of this particular form, I can come up with a way, an algorithm to figure out what my K matrix should look like. Okay, so in the context of 3551, people did Bode plot, Nyquist plot, and used Bode plot and Nyquist plot to design the lead and lag compensator for the systems, which is essentially equivalent to identifying what the K matrix is going to look like. Awesome. Now, because I know what A hat and B hat matrix looks like, I can design a K which satisfies the characteristic. Now, what I know is my x of t is equal to P inverse x hat of t yes, that's right, yeah. So P inverse x hat of t, I'm only able to observe x of t because that's what my original system is giving me. So my ut will become minus k p xt. This P matrix is right here. I got the P matrix from here. So I figured out what the P matrix looks like. I have this 1950s computer that can compute matrix inverse, that can compute the matrix. So I got this P inverse from there, and I got P from here, and then I can apply. Because this K matrix satisfies whatever criteria we had for the eigenvalues of A hat minus B hat K, it will also satisfy the eigenvalues of A minus BKP will have the same eigenvalue characteristics as A hat minus B hat K because they are similarity transform of each other. So these are the kind of ideas that we will be talking about fairly soon, probably next week, where we'll try to design the controller for this system, and then we'll try to pull it back to the original system, where we are going to use this idea that similarity transform of this will not change the eigenstructure of this particular matrix. And so this matrix is essentially a similarity transform of this matrix and therefore has the same eigenstructure as the original system. So that's what we are going to be doing in the future. And that's why we are studying the standard form, because I can come up with cool techniques to do control design for this. And using this idea, I can by default do control design for this complicated system. Okay. Any other question? Okay, so let's do I just want to cover very quickly what the observer canonical form looks like. So I have AC observable, So you can come up with, construct an appropriate P matrix for a single output. So you have a single output system. This is section 6.4.2. in the book. Okay, so what we have done today is we are able to identify how to convert one representation of the system into another representation of the system, so that if controller design can be done for the second representation, then I can use the same controller for the first representation as well. So this is the original system I started with. I have non-trivial, uncontrollable, and unobservable subspaces. So I'm going to use Kalman decomposition theorem, and I can decompose the state space into 4 different parts, wherein you have controllable and observable states and so on and so forth. I can do the control design for that, and then I can go back and apply that controller to the original uncontrollable, unobservable problem. Alternatively, I have a completely controllable system. So if it is completely controllable system, I'm going to apply this particular similarity transformation in order to get A hat and B hat matrix in this particular format. I can design the controller for this particular matrix, and then I can pull that controller back to the original system. If my system is completely observable, then I can convert the system into observable companion form, and I can design the observer for this particular system and then pull that observer into the original system. Okay, so that's the idea in all these things. There is a bit of a situation here, which is many of these techniques were designed for 1950s and 60s when computers were not that powerful, and so you needed to have that intuition about how to design controllers so that you can then design the controller for complicated systems. Unfortunately, I don't know what the relevance of teaching all this in today's world is, but it's part of the syllabus, so I have to teach it. So I hope there is still some relevance, but I really don't know where you would be applying some of these techniques. But hopefully you can learn from this stuff that people might be using. I don't know if you go to NASA or if you go to SpaceX, maybe they are still using the 1950s techniques of designing controller because it works. And you don't have to apply optimization and reinforcement learning and all that other advanced topics that we teach at OSU. Maybe you don't need that. Maybe this is all you need in order to make SpaceX go all the way to moon and come back. Maybe, right? So I don't know where exactly these kind of tools will be applied in the future. And remember, the reason why I'm teaching you is because I'm preparing for the next 30, 40 years of your career, not for 1950s career, but 2030 to 2060 or 2070 career. So hopefully you will find some relevance in the future, but I personally don't know where you will be applying some of these techniques because they were developed for 1950s when computation was very scarce, and now computation doesn't seem to be scarce. People are putting $50 billion in data centers. So maybe it cannot control the rocket that's going to the Mars. I guess then there is a reason for studying these things. Who knows? Okay. So that's all I have for today. We'll talk about controller design, which is, I think, chapter 8 from the book. I'm skipping chapter 7. I think chapter 7 is not, 7 and 8 probably is not important for us. And I'll move to controller design, which is chapter 9. So I'll talk about chapter 9 in the subsequent, like on Thursday's class. Thank you.